The next talk is a paper that received the Best Paper Award at NIPS, and it is my great pleasure to award this diploma and a check of $1,000 to the authors of the paper, Hong Nam Hung, who is going to present the paper here, and John Ducci from Stanford University.
Thank you. Thank you. All right. I'm Hong from Stanford, and this is based on joint work with my advisor, John Ducci. So the starting point of our talk is this article that popped up a few years back, which cited a research paper and said that liking curly fries on Facebook is associated with your intelligence. Now, I'm sure a lot of people in this room like curly fries, and I'm sure everyone in this room is very intelligent. But then again, who doesn't like curly fries? So it's probably the case that this observation, which seems somewhat non-intuitive, is highly non-robust to even small perturbations in the underlying data set. And to be fair, it was probably the writers who wanted to play this viral point up in their article, but the point I'm trying to make is that we want our research findings to be robust, and we want them to have little variance across different populations. Okay. So in typical supervised learning scenarios, what you do is, given a data set, you want to minimize your loss on this data set. More formally, the actual population problem that you want to solve is you want to minimize the expected loss under the underlying distribution P0. Okay. So throughout the talk, I'm going to use L to denote your loss, and X to denote your data, and I'm going to use theta to denote your parameters. Now, because the underlying distribution is usually not known, what you usually do is given a data set, x1 through xn, you take an empirical approximation of the population problem, and you simply minimize that. So this is what's known as empirical risk minimization. Now, in most cases, the empirical distribution is a random object, and depending on the random draw from the underlying population distribution, it can vary quite a bit. Okay, so if you put them all together, you can see that from one draw to another, the empirical distribution can look somewhat different. And in this case, we drew 25 samples, and you can see that it has something like 25% variation. So we want to be robust to these small perturbations in the empirical distribution. Okay. Now, again, our ultimate goal is to minimize this population loss. And what you usually do is the empirical risk minimization problem, which simply minimizes the empirical mean. Now, instead of just considering this empirical distribution, let's consider a whole bunch of distributions in this set script P. And let's minimize the worst case loss in this region. So today, what we're going to do is we're going to give a statistically principled way of choosing this worst case region so that it'll give us nice certificates of optimality for the population problem. And now, so intuitively, by opting to solve this worst case loss, what you're really doing is you want to have good performance, almost all the time, instead of just an average. All right. Now, the specific way we're going to do this is because we already know that the empirical distribution, despite its shortcomings, is a reasonable approximation to the population guy. We're going to set a neighborhood around this empirical distribution, and we're going to use that as our worst case region. So to define this neighborhood in the space of probability measures, you need a notion of distance. So we're going to use what's known as chi-square divergences. And using this notion of distance, we can define this neighborhood around the empirical distribution of radius rho over n. So visually what we're doing is, on the picture on the right-hand side, here you have a simplex when n is equal to 3. So that's the set of all distributions. And at the center, you have the empirical distribution. And by taking the chi-square divergence ball, what you're doing is you're essentially just taking an L2 ball around the center point, the empirical distribution, and you're using that as your worst case region. Okay. Another way to visualize this is by plotting the loss values at different data points and then sorting them. Okay. So that's the black line here. I've plotted the loss values of 50 different data points, and the blue line is the empirical distribution, your 1/50 weights. Now, I've also plotted the worst case distribution for this fixed data, And you can see that you're really upweighting the harder examples in your training process by opting to solve this worst case loss. All right. So again, this is our procedure. You want to minimize this worst case loss. And this is computationally nice because if you start out with a convex loss, then because maximum of convex functions is still convex, this worst case loss, this inner worst case loss, is convex in theta. So we can come up with nice stochastic gradient descent-like procedures that can solve this worst case loss as fast as just applying SGD to an ERM problem. So there's virtually no computational cost for opting to solve this worst case loss instead of the empirical risk. Right. So more concretely, you can think of this as a minimax stochastic game. And at each iteration, the adversary wants to sample the harder examples in your data set. So at each iteration, you sample a data point from this adversary, and then you do an SGD step. And then you update the adversary via coordinate ascent step on the probability vectors. And by storing these probability vectors of the adversary in a clever data structure, you can ensure that the projections onto this chi-square divergence ball, the worst case region, is efficient. Okay, so now I'm gonna give a theoretical motivation and a theoretical analysis of what it really means to minimize this worst case loss. So we're gonna start with the classical bias variance trade-off. And one way of making this concrete in this stochastic optimization setup is by using what's known as empirical Bernstein's inequality, which says that you can bound the population mean, your population objective, by the empirical mean plus the square root of the empirical variance over n. And given this upper bound on your population objective, which you can't compute, you get this urge to want to minimize this upper bound instead. So this is exactly what Maurer and Puntil suggested a few years back. And this is what we're going to call variance regularization. And the nice thing about this procedure is that you're optimally trading off between bias and variance. And by virtue of doing so, you're optimizing a 1/n approximation to the population objective, which is a tighter approximation than the usual ERM, which only minimizes the first bias term. Okay, so this seems like a good idea. However, there is a minor issue in that even when you have a convex loss function, the variance of the loss may be highly non-convex. So here I've plotted the variance of this simple L1 loss in one dimension. And you can see that it looks pretty funny even in this one-dimensional example. So who knows what it looks like in higher dimensions. Now, our first main result of the paper says that our worst case loss, our robust loss, is in fact exactly equal to this variance regularized objective with extremely high probability, as long as you have enough variance in your loss. So this left-hand side, the robust loss, which we saw that was computationally efficient to solve, retains all the nice statistical properties of regularizing by variance. And the right-hand side can be, in general, non-convex. So this is somewhat a surprising result. Okay, so by virtue of trading off optimally between bias and variance, what you can show is a performance guarantee for the robust solution. So if you let theta hat Rob be the robust solution of our procedure, then you can show that the population performance under this robust solution is no worse than this optimally traded off quantity with the population mean and the population variance. Okay. So we're going to try to dissect this a little bit in the next slide. But before we do that, and one nice thing about this theorem is that it gives us a principled way of choosing rho, the size of your worst case region. So rho can be the complexity of your model class. So you can think of them as a log covering number, or you can also think of them as localized Rothenberg complexities. So these nice learning theoretic notions go through in this variance regularization setting as well, with a bit extra work, of course. All right, so this was our guarantee for our robust procedure. And let's compare that with the usual guarantee that you get for the ERM procedure. Okay? So for the ERM solution, you can usually show a bound that looks like this. And if you compare the two, you can see that if the variance term is smaller than this uniform upper bound on your loss times the mean, then the first bound will be tighter. Okay? And this is often the case because this big number m usually depends on global information, such as the size of your model class and a uniform bound on your random vectors. So in the paper, what we actually have is an explicit example where the robust procedure achieves the fast rate of convergence at the rate 1/n, but the ERM procedure still suffers the standard 1 over square root of n rate. All right. Now let's try to understand what a robust procedure does empirically. Okay. So recall that by opting to solve this worst case loss, what you're doing is you're really upweighting the harder examples in your data set. And it's often the case that if you have a rare class of instances, you have high loss on those rare classes. So you sort of expect improvements on this rare and harder class of instances by using our robust procedure. So here I have a document classification problem where you want to classify a document into any subset of these 4 categories. So it's a multi-label problem. So we're going to use 4 different binary logistic classifiers, and we're going to aggregate them to make a prediction. And for both the ERM and the robust procedure, we're going to use L1 regularization with radius 1,000, which was chosen based on cross-val based on the ERM solution. And we're going to use precision and recall to evaluate their performances. Okay? Now, in this data set, there is a category that has a relatively fewer number of examples compared to the other 3. We sort of expect that it might be harder to classify instances that are in this economics label compared to the other 3. So let's compare it with your performance on the most common label, the corporate label. Okay? So here you can see that the ERM solution have something like 90% recall, so here higher is better. And as you try, so you're doing pretty well to begin with. And as you increase rho, as you try to be more robust, or as you try to regularize by variance more, you can see that performance increases by a tiny bit, and then it starts degrading because you're trying to regularize by too much. Okay. Now, on the rare category, you can see that your performance, you start at something like 68% recall. So you're significantly worse off on this rare category compared to the common category. And as you try to be more robust, you can see this significant improvement on your performance on this rare label. So you get from something like 68% to 80%. So overall, you can see that you get this significant performance improvement on the rare category. So we really are doing well almost all the time instead of just on average. So in the paper, we have a bunch of other experiments which sort of illustrate this point in more detail. All right, so to summarize, in this talk, we gave a statistically principled version of a distributionally robust formulation. And we show that it's a convex procedure for regularizing by variance. And variance regularization was nice because it traded off optimally between bias and variance. And by virtue of doing so, it was optimizing a 1 over n approximation to the population objective. So this was a tighter approximation than your usual ERM loss. And because of these nice properties, you could see that the robust procedure had nice generalization guarantees. And empirically, we saw that the robust procedure improved performance on the harder instances. So we really do well almost all the time instead of just on average. Thank you for your attention. And please come to our poster tonight. The poster number is 212.
There is time for questions.
Yes, hi. So I didn't get what was the computational complexity to do the subgradient on the P
Good.
part. Is it linear in n?
So it's essentially the same complexity up to a constant of applying SGD to the ERM problem. So this constant depends on rho, the size of your worst case region.
Hi. Does this actually help you with adversarial examples?
Good. We haven't tried it with this exact formulation, but there's other worst case regions that you can set with different notions of distance. For example, the Wasserstein distance, in which case it definitely does help against adversarial attacks. We actually have a paper on that.
If there are no more questions, then let's take the speaker again.